chapter number 1 is a power semiconductor devices. Or it is also known as a switching devices. So important points from the chapter. Energy loss and power loss during transition state. We represent it with ESW, that is the energy loss, and power loss is a PSW, right? ESW means switching energy loss, or it is also known as a transition state energy loss, and power loss during transition state, it is denoted with a PSW. Important point. Next important point is a conduction state power loss. P average, right? So for conduction state power loss means it is also known as a on state power loss of a device. In that, if you recall, we are having the 3 piecewise modelings. One is a pure resistor, second one is a constant voltage drop, and third one is a combination of pure resistor and a constant voltage drop, right? So for all those 3 models, we are having some power expressions. So conduction state power loss. Third important point is a composite switch, very important. Composite switch. In composite switch, operating point location on VI plane is important. Check your GATE 2023 question paper, one question they asked, and before that I think 2 years back, that is GATE 2021, somewhere they asked one question recently on composite switch. Next is in SCR, we are having the minimum gate pulse width required, some numericals related to the minimum gate pulse width required. Minimum gate pulse width required to turn on SCR. To turn on SCR, right? So these bits are very important. I am saying very important, right? Next to that, few bits are there, like protection of SCR. In protection of SCR, yeah, as long as gate examination is considered theory questions, there is a less possibility of getting a theory question. But some questions were having related to the protection of SCR, like RC snubber circuit given and calculation of the value of capacitor, calculation of the value of the resistance, right? Even some of the numericals were having where the di by dt inductor is present as well as your RC snubber circuit is also present. So combination of those two, okay, both are present. So at that time also how to solve the numerical, that type of question you can expect. Next is gate characteristic of SCR. Yes, gate characteristic of SCR. So these are some important bits. In that, first 4 bits are very important, and next 2 are comparatively important but not very important. All right. So now let us discuss. Let us start the revision of the chapter number 1, power semiconductor devices. Okay, great. So if you recall, in power semiconductor devices, yes, we started with the difference between signal level devices, power level devices. That is the one part. You will not get any question on that. Okay. Next, energy loss. Okay. Energy loss during a transition state. During a transition state in a practical switch. So in that again we are having the two types, turn on transition and turn off transition. All right. So first, energy loss during a turn on transition. ET on, right? So in that, if you recall, we derived the expression for energy loss when during the same time interval voltage and current are varying linearly, but one with a positive slope, second one is with a negative slope. This is the turn on transition. After this, it is like your switch is in a on state. Before that, it is a off state. This is V and this current is I. Right? Check. Turn on transition means transition from off state to on state. So initially switch is in off state na. What is the voltage across switch? Non-zero. Current for the switch is a 0. Right? At this point we have started turning on a switch. My switch is taking this much time to turn on na. And during this turn on transition time, your switch current increase linearly, switch voltage decrease linearly. So for this type of plot, we have already derived the expression for energy loss. What is the expression? Yes, we have written ET on equal to 1 by 6 into V into I into T on. 1 by 6 into V into I into T on. Right? Important expression. During the same time interval, if voltage decrease linearly, current increase linearly, the energy loss in a switch during that turn on transition time is 1 by 6 into V into I into T on. But be careful, here V is nothing but a voltage across the switch during off state, and capital I is nothing but a current from the switch during its on state, right? During its on state. Similarly, we are having the expression for ET off also na, energy loss during turn off transition. During turn off transition, simply this will reverse na. So during turn off transition, energy loss during turn off transition. Yes, second. ET off. Yes. During turn off transition, Yes. During turn off transition, current from the switch decrease linearly, voltage across switch increase linearly, right? And during this time interval, what is the energy loss? Yes, we derived the expression earlier. Et of equal to 1 by 6 into V into I into T of, right? Important expression. This is energy loss during turn off transition. 1 by 6 V into I into T off. In previous case, it was 1 by 6 V into I into T on. There is a similarity. Alright. Next, what is the total energy loss? ESW. Yes, very good. ESW equal to ET on plus ET off, na? Right? ET on plus ET off. So it is equal to 1 by 6 into V into I into T on plus T off. T on plus T off. Right? So based on these expressions, ET on, ET off, repeatedly they have asked the questions in a gate examination. Alright? Yeah. Next, how to find the switching power loss? That PSW. PSW is a average power loss. It is not instantaneous. It is average power loss during a transition state. So I am writing here PSW equal to, yes, it is ESW upon switching time, na, TSW. And 1 by switching time we replace it with the switching frequency. So it is ESW into FSW. So switching power loss is equal to ESW into FSW. Important expression. Right? PSW. Yeah, so these are the expressions for energy loss and switching power loss. During same time interval, one is increasing linearly, second one is decreasing linearly. During the same time interval, yes, during the same time interval, one is decreasing linearly, second one is increasing linearly, right? So that is the one case. Even we discussed the cases where during the some time interval, suppose if voltage is constant, current is changing, then how to find the energy loss? Let us discuss one case. Suppose if you are having the plot like this, suppose this is voltage, yes. So suppose if they give this type of the plot and if they ask what is the ET on, how to find? Yes, we have written na, ET on equal to energy is nothing but integration of power. Energy is nothing but integration of power. And that integration over which time? Over the time T on only, na? Over time only T on. So we wrote it as 0 to T on. So it is integration 0 to T on. PT on is nothing but voltage across switch into current flowing through the switch into dt, na? Then what we did during the time T on, your current is constant, na? So that constant current ISW were taken outside. So it is ISW integration 0 to T on VSW into dt. So what this term indicates? This indicates area enclosed by the switch voltage, na, VSW. This is area under VSW. Switch voltage karo, VSW means switch voltage karo. During which time? T on. During T on. Next, so ET on equal to, yes, what is ISW value? During this time interval, my ISW is a constant, na? So we replace that with I into, this term indicates area under VSW. So over time T on, My switch voltage is this curve. So what is the area enclosed by this switch voltage? That will form a triangle na? Area enclosed by the switch voltage waveform. Over which time? Over time t on. So that enclosed area is nothing but area under this triangle. How to find that area under triangle? 1 by 2 into height of the triangle is v into time is t on. Alright? Into t on. So it is equal to 1 by 2 into v into I into t on. Right? So if during the same time interval one is constant and other one is changing linearly, then how to proceed? Then you need to take the help of this area under that one triangle you will be getting and into the constant term as it is. Alright. So they ask the question on these type of plots also. Okay. So two types of the questions you can expect on energy loss during transition state or power loss during transition state. Two types of the questions. One is during the same time interval, one is changing decreasing linearly and other is increasing linearly, and second is one parameter is a constant and second is changing. All right. Yeah. So this is the energy loss during a transition state. This question they asked in a GATE 2014. Figure shows 4 electronic switches 1, 2, 3 and 4. Yes. Which of the switches can block voltages of either polarity applied between terminals A and B? Voltages of either polarity means bipolar they are asking. When the active device is in off state, right? So when active device is in off state, which of these switches out of these 4, which switches block the voltages of either polarity? Either polarity means forward voltage as well as reverse voltage. So they are asking bipolar. Our task is out of these 4, which are the bipolar devices, bipolar switches, that we need to find. Yes, can anyone? Yeah, some of you have already answered the question. Good. Yeah, you can post your answers also, right? Yes. Okay, right. Yeah. So how to check which of these switches block the voltages of either polarity? So let us focus one by one. Check. First thing is, let us consider first switch. This is a combination of your IGBT and a diode, right? So is it a composite switch? Yes. Composite switch means it is a connection of 2 or more switches. So here 2 are present now, so that's why it is a composite switch. IGBT and diode connected in anti-parallel, so that is a composite switch. Now here, out of these 2 switches, which switch is an active switch or which device is active device? IGBT and diode, if I compare, which device is active device? Active device means your semi-controlled devices or fully controlled devices, those are active devices. And uncontrolled device is a passive device. So uncontrolled is only one we are having, that is a diode. So diode is a passive device. All other remaining whatever the devices we are having, all these are your active devices. Okay. So this is your active device, IGBT. This is a passive device, right? So now here, in order to find the check whether this is blocking the forward voltage, reverse voltage or not. For that, simply apply the forward voltage first. First apply the forward voltage between terminals A and B. Suppose between A and B terminals, I have connected the external supply. Positive plate of the supply is connected to terminal A, negative is connected to the terminal B. And consider active device is in off state. When this device is in off state, means it is an open circuit here. If here it is open circuit, whether any current will flow through IGBT? No. Current will try to flow through this diode, but diode will not allow reverse current. So when active device is in off state and if this type of forward voltage is maintained, then the current is not flowing either through IGBT or through diode. The meaning is my composite switch is blocking the voltage. If current is not flowing, the meaning is switch is blocking the voltage, right? So if you maintain forward voltage and if this is in off state, no current will be flowing, means it is blocking the forward voltage. Similarly, now maintain the reverse voltage. What will happen if I maintain reverse voltage? If I maintain reverse voltage, means positive plate of the supply is connected to the B, negative plate is connected to the A. So as soon as I connect the positive plate of the external supply to the terminal B, negative to the terminal A, immediately my diode, this diode will start conduction na? Diode will become forward bias, and when diode starts conduction, the current will flow. So current is flowing, the meaning is your composite switch is unable to block the voltage. So this switch will not block reverse voltage. So this is only unipolar switch. This is unipolar. Yeah, second, IGBT and diode in series. Check, maintain the forward voltage. When I maintain forward voltage and consider active device is in off state. Active device off means open circuit. When this is in open circuit mode, whether current will flow from A to B? No, current is not flowing. The meaning is my composite switch is blocking that forward voltage. Similarly, maintain the reverse voltage. Maintain the reverse voltage. When I maintain reverse voltage, means here it is minus, here it is plus. What will happen? When I connect this type of external supply polarity, plus higher potential here, lower here, independent of status of this IGBT, this diode will become reverse bias na? This diode will not allow reverse current. The meaning is my composite switch is unable to carry the current. Current is not flowing means it is blocking the reverse voltage. So this is a bipolar. Third is, this is not a composite switch, this is normal one device na, SCR. We know SCR is a bipolar unidirectional, so it is a bipolar. Here the question is only related to the voltage blocking, right? So bipolar. And what about this one? SCR and diode in anti-parallel. Check, when you maintain the reverse voltage, immediately this diode will start conduction. So this switch is not having the reverse voltage blocking capacity, so it is a unipolar. So switch number 1 and 4 are unipolar, switch number 2 and 3 are bipolar. So switch number 2 and 3, option C is the correct option, right? Check, similar type of questions were discussed. Okay, yeah, so here actually we are having less time, so I cannot go in depth key that procedure. Okay, so in short I am trying to give the answer. Yeah, so 2 and 3. Yeah, next, this question they asked in GATE 2016. Important question. A steady DC current of 100 ampere is flowing through a power module S, D as shown in figure A. So this is your power module. Means it is a composite switch only. IGBT and diode connected in anti-parallel, that is forming a composite switch. Yes. A steady steady current of 100 ampere. Yes. 100 ampere current they have given, and check the direction of the current. Current direction is upward na? They have given current direction is upward. Next, the VI characteristic of the IGBT and the diode are shown in the figure. Here they have shown the VI characteristic, right? Here it should be VT, huh? And this is also VT. Next, VI characteristic of IGBT and diode respectively. The conduction power loss in the power module in watts is, they are asking the conduction power loss, that is on state power loss, means P average. How to find the on state power loss? Recall piecewise modeling. For every modeling we are having one expression na, P average. So from that which modeling you need to select and which expression you are required to use, that you need to understand here. Please listen. Here it is given that this is your switch and the current from the switch is in upward direction. Tell me, if the current flowing is in upward direction, out of this IGBT and diode, this current will flow through which device? Whether this current will flow through IGBT or through diode? Yes, this current of 100 ampere will flow through, whether it will flow through S or it will flow through D. If current is upward means that current will flow through diode only na? Yes, no. So here diode will be in a conduction mode. So when 100 ampere current is flowing through the diode, then what is the conduction state power loss in that diode they are asking, right? Conduction state power loss in this SD module or power module is nothing but power loss in diode only, because no current is flowing through IGBT. This current is only flowing through your diode, alright. So 100 ampere constant current, DC current is flowing through the diode. Then how to find the power loss? Diode belongs to third modeling na, VT in series with R1. So you need to find first VT and R1. Once you get Vt R1, you can find power loss. Yes, Vt and R1. This current is I. How to find Vt? For that they have given this plot. This is for diode, VI characteristic of diode. So Vt means what? The Vt means this minimum voltage required to turn on diode. How much voltage they have given? 0.7 volt. So Vt in this piecewise modeling, this Vt is nothing but this 0.7. And R1 means resistance na. So resistance, for that they have given dV by di. dV by di means it is a ratio of voltage to current na. Ratio of voltage to current means resistance, right? So that is nothing but 0.01 ohm. So that R1 is nothing but 0.01 ohm. So instead of directly giving Vt and R1, here they have given in form of this plot. Okay. So what is Vt? 0.7. And what is R1? 0.01. So here Vt is 0.7. Yes, Vt is equal to 0.7 volt and R1 is 0.01 ohm. Now what is the P average? Vt into I average plus I RMS square into R1 na? Yes, so it is equal to 0.7 into I average. 100 ampere constant current is flowing na? So what is the average value? 100. And I RMS, if current is a DC current, its RMS value, its average value will be its amplitude only, that is 100, into R1 is 0.01. So simplify this, you will get P average. Yeah, it is a 70 plus 100 na, so it is 170 watt, right? So conduction state power loss is a 170 watt. Yes. Yeah, a simple question, GATE 2017 theory question. For the power semiconductor devices, IGBT, MOSFET, diode and thyristor. Here thyristor means SCR. Huh? By default only if they specify thyristor, means you need to take it as SCR only. Strictly speaking, thyristor is a family of devices, but most popular member of a thyristor family is a SCR. So that's why we can use the words SCR and thyristor interchangeably, right? Yeah. For the power semiconductor devices, IGBT, MOSFET, diode and thyristor, which one of the following statement is true? All the four are majority carrier devices. Check. Question is related to majority minority. Tell me, out of these four, which devices are majority, which are minority? MOSFET, majority. Diode, minority. SCR, minority. What about the IGBT? Check your note, your difference between majority minority charge carrier devices. At the end we have written note in notes. What is the note? IGBT is a minority charge carrier device and it is having a positive temperature coefficient. Okay. So yeah, IGBT also conductivity modulation process is present. So that's why it is a minority. So MOSFET is a majority carrier device, whereas IGBT, diode, thyristor are minority carrier devices. Option D is the correct option. Yes. Next, yeah, same GATE 22. A charger supplies 100 watt at 20 volt for charging the battery of the laptop. The power devices used in the converters inside the charger operates at a switching frequency of 200 kHz. Which power device is best suited for this purpose? 200 kHz frequency given. Which device is suitable? MOSFET na? Yes. Highest frequency. Yeah. GATE 2014. The SR in the circuit shown has a latching current of 40 milliampere. A gate pulse of 50 microseconds is applied to the SCR. Maximum value of resistance in ohm to ensure successful firing of the SCR is. Yeah. So this question we already discussed during our classroom sessions. So here I am considering current as I1 and I2 na. Our task is to find the value of resistance R for successful turning on of a SCR. What is the gate pulse width given here? 50 microsecond. So TP given 50 micro. Next, latching current given 40 milliampere. And our task is to find the value of resistance R. Right? How to find? Simply here, for t greater than 0, draw the circuit. Right? For t greater than 0, SCR will be in on state, na? SCR on state, then I is equal to simply I1 plus I2. We need to find expression of I1, expression of I2. Yes, so I can write here. For t greater than 0. What is I1? I1 is the current flowing through this REL branch, na? SCR on state, current in the I1 branch. Check across this REL branch, 100 volt voltage is connected. So when DC voltage source is connected across REL branch, what is the current expression? Supply voltage upon branch resistance into 1 minus e to the power minus t by tau, that is minus RT by L. So here I am writing I1 equal to 100 by 500, Vs by resistance, na? So it is 100 by 500. Into 1 minus e to the power minus RT by L. What is the resistance value? 200 millihenry. 200 milli means 0.2 Henry. This is I1. 1 minus e to the power minus 500 into T by L. Right? So it is equal to 1 by 5 means 0.2 into 1 minus e to the power minus 2500 into T, na? This is I1. What is I2? I2 means current here, which is equal to 100 by R, na? Simple, 100 by R. So 100 by R. So I equal to I1 plus I2. So it is 0.2 into 1 minus e to the power minus 2500 into T plus I2 is 100 by R. Right? This is current expression for the current flowing through the SCR. Right? And now how to find this resistance value? Check at, we have written at T equal to TP, I equal to IL. Your current plot will be like this. Yes, what is the value of current at T equal to 0? Put T equal to 0. E to the power 0 is 1, 1 minus 1, 0. This term will be 0. Only 100 by R. So at T equal to 0, this current will be at 100 by R. As time increases, this term will decrease. So 1 minus this decreasing term, difference will increase. This current will increase. Right? So addition will be increasing. So current will increase. At T equal to infinity, e to the power minus infinity, 0. So 0.2 plus 100 by R. So final value will be 0.2 plus 100 by R. Right? So when current increases from this 100 by R to this 0.2 plus 100 by R, somewhere it will cross to latching current, na? So we need to maintain the gate signal till SCR current reaches which value? Latching current. We need to maintain the gate signal till SCR current reaches latching current. So we need to find the value of resistance. TP they have given. Resistance value we need to find. So how to find? Simply put, at t equal to Tp, I equal to IL. In this expression, at t equal to Tp, I equal to IL. At t equal to Tp, I equal to IL. So I can write here IL equal to 0.2 into 1 minus e to the power minus 2500 into Tp plus 100 by R. Check Tp they have given, IL given na, put the values and find for, simplify for R. You can simplify this. After simplification you get resistance value as 6060.60 ohm. Okay. Yes. Yeah. So here they ask the questions, this type of questions. This question is somewhat difficult question because here two parallel branches were having. Some question they asked only one branch is present. Suppose if I remove this resistance branch, then that will become single loop circuit. They ask the questions based on single loop where only pure inductor is also present, like DC voltage source, SCR and only inductor. That type of question they asked. Second, DC voltage source, SCR and RL branch, single loop. That type of question also they asked. And next, two parallel branches. These type of questions also they have asked. Okay, right. So you can expect question on purely inductive load, on RL load, right? Like remove resistor, only RL will be present, single loop and RL. And like parallel branches, RL and R. This type of, okay, right. Next, yeah, GATE 2016, they have asked this question. Yeah, in this plot there is one correction. Let me correct it first. Yeah, actually the plot is like this. The voltage Vs across and the current Is through a semiconductor switch during turn-on transition are shown in the figure. So they have given this turn-on transition. During turn-on transition, Vs and Is plot. Vs means voltage across switch, Is means current flowing through the switch. Next, the energy dissipated during turn-on transition in millijoule is. They are asking ET on. What is the ET on? They are asking. So first we need to identify out of this T1, T2, which time indicates your ET on. So check here. Yes. Before this point, current 0, voltage non-zero, means switch is in a off state na. Current 0, voltage non-zero means switch off. After this point you can check. Current is constant, voltage is 0. Voltage 0, current non-zero means switch has successfully turned on. So before this switch off, after this switch on. In between these 2 points, voltage also non-zero, current also non-zero. So it indicates your transition state. It is your transition state. Alright. So here off to on transition means this total is your turn on transition. So I can write here T on equal to ET1 plus ET2. ET1 plus ET2. So we need to find the ET1 and ET2. Once we get ET1, ET2, we can find the ET on. So how to find ET1, ET2? Yes, ET1 equal to, check during the time T1, voltage constant, current is increasing linearly. So here you should not use that 1 by 6 expression. That 1 by 6 V into I into that time T on or T off. That expression is only for during the same time interval, one decrease, second increase, or vice versa. But here one is constant and second is increasing linearly. So how to simplify? By finding the area na? So I can write ET1 equal to, yes, it is integration 0 to T1 Vs into Is into dt. Here Vs is constant, so 0 to T1 Is into dt. Yes, here is into dt. This term indicates Vs is a constant, integration over 0 to T1 is dt, that indicate area enclosed by is curve over which time? T1 time. So that will give me the area under triangle. Area under triangle is 1 by 2 into T1 into this height is, this is 100, this is 50, so total is 150, right? So here 1 by 2 into T1. Yes, Vs is a 600 into 1 by 2 into T1. T1 is a 1 micro into 150. Yes. So it is a 45 millijoule. ET1. Right? And similarly ET2. ET2 equal to integration 0 to T2. Only over time T2 I am taking. Vs into Is into dt. Yeah. Over T2 time. Over time T2 means from this point to this point. Over time T2, current is constant 100 ampere. Voltage is decreasing linearly. So here again check current constant now over T2 means take that current Is outside. So that Is I can take outside. And this integration 0 to T2 Vs into dt. This will give me the area enclosed by Vs. So Is is 100. Area enclosed by Vs is area under triangle 1 by 2 into 600 into T2. That is 1 micro. So this will be 30 millijoule. ET2. Right? ET1 and ET2. Right? Now you can add these two, you will get ET on. Therefore ET on is equal to ET1 plus ET2 is equal to 75 millijoule, right? 75 millijoule. All right. Yeah, let us discuss this question. This question is from GATE 24. If the following switching devices have similar power rating, which one of them is the fastest? So out of these, which one is the fastest device? GTO, SR, IGBT, MOSFET. MOSFET is the fastest, na? Fastest means more operating frequency, right? Less transition time. So MOSFET, right?